Let's get this going. As introduced, my name is Matt Schutze. I'm the product manager at a company called Azul Systems. We have a budding relationship with DataStax, and we've been doing some work with Cassandra predominantly, and Spark and some other things. So I'm very excited to be here to give this little introduction to what we're doing and see hopefully if you guys find it interesting as well. First off, does everybody know who the four main Java vendors are in the world? Points for the big one. Who's the big one? Oracle. That's right. Who's number two? Who rolls their own JVM? IBM. Yeah. Can you name two more? Nope. I'll give you a hint. It's in the upper right corner of the slide. And the fourth is Red Hat. They actually have their own. So most people ask, what do you do? We're a Java vendor. We actually build Java virtual machines. But we'll get into that. So today I want to introduce who is Azul, what is our Java virtual machine product. It's called Zing. We're going to go through some use cases for Cassandra where we talk about latency, which is basically underpins response time. And then look at some measurements and how you actually properly measure latencies in a system, and how statistics, which are also, we call them damn lies, can affect your feelings about the latencies that you measured. And so doing it properly and is using the tools that are available is a bit of an art form. And we're trying to remove those lies and make people tell the truth in their measurements. And then I'm going to do a little bit about the CAP theorem. Anybody know what the CAP theorem is? Yes. Okay, kind of underlies the foundation of why Cassandra works the way it does. And then we'll have time for some Q&A. I'm going to fit all this in half an hour. Good? Excited? Punchy? Ready? All right, good. Yes. All right, so Azul, all we do is Java. We are a company that's 100% invested and involved in building Java virtual machines. We've been around for over a decade, and our first our first product was a hardware appliance. Back in the day when Java turned out to be useful on servers, after applets and cute little tumbling dudes, they figured out it works really well on servers. The servers in the early 2000s were kind of not great for consistent high-power workloads. So we built 3 generations of a multi-core hardware system. We built the chips, we built our own Linux distro based on Debian, we built our own Java virtual machine, we put it all on a big honking 854-core machine with 2 terabytes of RAM and sold that and made a nice little business out of it. Until the 4th generation would cost us more to make than it would to switch to just running on Intel, so that the hardware side of our business sort of evaporated with the new Intel multi-core chips. But we converted that product into what is today Zing. Zing is a Java virtual machine. Actually, it's a full JDK with a runtime environment and developer tools. But basically, it's a replacement for the JVM or Java that you get from the other vendors, whether it's Oracle, IBM, or Red Hat. And it runs on commodity Intel. We couldn't beat Intel, so we joined them. We just sit on top of their 64-bit hardware today. After a couple years of that in the market, it's starting to take off and it's getting interest. We decided to sell one of our byproducts. On the way to build Zing, we have to build OpenJDK too. Everybody familiar with what OpenJDK is? That's the open source project in which Oracle and the rest of us Java vendors build the next version of Java. So we just take that source, build it, and now have a plain old Java called Zulu. And that's a whole other topic, but it's part of our product mix. But really, our claim to fame and what we're known for, stemming from Vega, moving on through today into Zing, is for low latency and continuous, predictable performance in Java execution on widely different scales. We now have a version of Zing that's that's RTMing tomorrow that can handle a terabyte heap size without adding garbage collection clauses. So that's the kind of scale we deal with, from 8 gigs of RAM up to a terabyte and everywhere in between. We can actually run that without introducing the normal stalls and jitter and hiccups that can plague the other JVM vendors' options, including OpenJDK, therefore including Zulu. the question always comes back to us, or in general, is people are using Java for low latency. That doesn't seem right. Java's a managed language. It's got a garbage collector. It's got a jitter. Is it really fast enough for low latency, like millisecond or sub-millisecond performance? And we say the answer is yes. And here's why. In terms of the Java virtual machines in the world, one of the basic design principles was write your source code once, but run it anywhere. So the Java virtual machine is that piece of technology that lets you do that. That portability comes at a cost for us Java vendors. We each have to build a JVM on a platform, so you can then write Java code that just compiles and works. But then the truth is, we Java vendors, even though we adhere to the portability rule, we fight like cats and dogs to differentiate our JVMs, because they are not the same. They have different workloads in mind. They have different audiences. They have different development and operations cares. So just because you pick one because it felt like it was free off the web doesn't mean it's going to be the right thing for your application. And your performance, your perceived and measured performance can vary. It's not necessarily the same, even between things that ultimately are very similar. A JVM's got boatloads of switches in it that let you pick different garbage collectors, different settings, different ratios, different thresholds. So, and if you change your code, suddenly some of those switches might be wrong. So you have to be careful how you balance the setup, the configuration of the JVM, let alone the JVM you picked in the first place. Plus, the other variables have to do with just basic computation. How much memory are you giving your app to chew through? How fast are you allocating objects? And how fast the JVM can pick up any objects that are turned to garbage. The objects that are no longer in scope, are no longer reachable by any other to the GC routes. So, and basically you want to free up that unused space, reclaim it to reuse for new allocations. All of those things can affect actual fielded performance of an app. So, fact or fiction, all JVMs have something called a stop the world mechanism in their garbage collector. Basically that means you're running code, your Java threads. We call you guys mutators because you're mutating the memory graph. Your threads will all stop while the garbage collector does some work. And for almost every garbage collection cycle out there, the CMS, the garbage first, the parallel new, the balanced, the new one, that's Shenandoah. There's a bunch of different strategies, but none of them can keep up with a very fast allocation rate. And usually there's a penalty. The pauses get worse as the amount of memory you give the system gets larger. Our rule of thumb is a second per gigabyte. So if you had a 100 gigabyte heap, you'd be waiting a minute and a half on a full GC pause. So that's typically not good to have pauses up to a minute in an application. We've just got to pick a customer here that we're talking about on the way in there, 15-minute pauses before we put in Zing. Drop it away. I think that was not here, that was in Louisiana, is that right?
Yeah.
Yeah, New Orleans. So that's the kind of real world scenario that we're trying to combat. Take away those otherwise, nuisance pauses if your heap is low, but application breaking pauses if your heaps are high or your data sets are high. So the Azul Zing JVM is based on its very first principles are take away pauses. Take away pauses by taking advantage of multiple cores on boxes. You can't buy a server today that's not multiple core, I don't think. And most of our customers are buying at least dual socket, 8 to 15 cores per die, and often much larger. And how do you take advantage of all of those resources and all of that memory without suddenly introducing pauses? We only know of our garbage collector as having solved the pause problem, doing everything possible in parallel and not freezing your JVM threads for longer than fractions of microseconds even. We have an internal benchmark of 55 microseconds is the worst possible time to get to the point where you can change memory. So that's pretty fast compared to other apps and other GCs which can take minutes. We talk about latency a lot. And this is the kind of graph we look at when we talk about latency, which is the time it takes not just for something to respond to a request, but basically the time it takes for useful work to start once a request is sent in. The round trip time might include other hops, so you can't necessarily call this end user response time. But the first part of any transaction is how long does it take to set up that transaction, let alone do the work and respond. So this is the best case. The best case is when the JVM is frozen. You're not going to get any faster than that because no work is happening. This happens to be a telecom app, which when you look at the peaks, those are all, we call those hiccups. They are little blips in the Java runtime where garbage collection is happening. So your useful work has stopped. But for the most part, 99% of the time, this is really rocketing fast. It's 60 microsecond latency, very fast. But sometimes it's very slow. The worst case here is the red bar. It's 23 milliseconds. So the worst case is 30,000 times worse than the best case, or the normal, the bulk, 50%, the median case. And these charts happen all the time because there's garbage collection is not noise. It's a phase change from something is running to where something is not running. And the duration or the length of them happens to correlate with how much heap you've got. So, and this is only like a, 600-second run, so 10 minutes. We generate plots like this all the time to try to characterize the latency of a system from inside the JVM. This is actually a tool we have that can sit inside of a running Java program and come out with these time hacks to know what your worst case latencies really are. So, introducing Zing. What is Zing? Zing is another JVM. You install Java, you have a Java home folder, it's the same thing. You can install Zing on a Linux box, you have another JVM. You can point your Java home, point your apps at that, and it'll run. Unchanged. Virtually, your code does not have to change. It's pure Java. It's certified 100% compatible, Java 6, Java 7, Java 8. But what it does is lets you improve that consistency of response time. So instead of having outlier latencies that are bad, they're all supposed to be good, or at least within your SLA, whatever that turns out to be, your service level agreement. So, financial services industry is a good example of who uses Zing today. If you have very high application throughput where sustained allocations are fast, therefore garbage collections are also fast, it's a good match. And then anything that have to do with large memory that otherwise would choke because of the pause times is a good candidate. Again, we tried out financial services, but real-time ad placement, the personalization that we were talking about before, that's all very, very relevant. The other is the time to deployment. Because it's Java. You write Java or Scala or any of the other JVM language codes with no change. You're pointing it at a different JVM and you run. So that means it's good for portals, it's good for Cassandra or other big data engines, and for search like Solar. We'll get to that when we get to examples. So do you ever follow that? I mean, that was kind of a whipsaw through Java and why we care about latency and what Zing is. So if that's the first time you've ever heard that, welcome. You're now part of the Zing family. Hopefully it'll sink in. And I've got actually some handouts back by the drinks and little cards if you want to do a trial for Zing, we can do that. But now, so that's a lot of noise. Let's see some data. Let's see some proof of this magical pauseless garbage collector. We've got a couple of examples, and this one comes from a foreign currency exchange based in the UK, who's built their entire infrastructure for their platform, both feeding market data to brokers and market makers, and actually executing trades, currency arbitrage trades. And they were already decided to implement their entire exchange on Java. But when they ran out of steam trying to remove latencies by tuning Oracle JDK, they decided to try Zing. It was a long engagement, both in terms of their understanding of how to configure things for absolute screaming hot speed, but also trust. They're an exchange, they're financial services, they needed to build in some trust working with us as a vendor and with the JVM as a product. But we did some pretty incredible work. They had already had a very tightly engineered matching engine. The matching engine, that's the thing that says, I want to sell at this price and I agree to buy at that price. So that's kind of the heart of every type of trading exchange platform, no matter what the asset class is. Be it stocks, commodities, whatever. And they had already, they were already having these GC pauses that they had beaten down pretty well, 4 milliseconds every half a minute. Still pretty frequent and not the best. We got that down to 1 millisecond every 2 hours. So that's a significant reduction both in scale and frequency. On the other systems that weren't the matching engine, that were just sort of part of the balance of plant, they had things that were 50 every 30 seconds. So again, pounding rapidly. We got those down without much work to get down to 3 milliseconds every 15 minutes. So we're taking this scale down to millisecond level. And then they had these big gargantuan pauses that could be half a second, which is forever in terms of a trading platform. They're gone. And those turned out to be not in the matching engine and not in the gateways that feed it, but in fraud detection and other things that were on the back that if they started to suffer, could force back pressure onto the the low latency path. So eventually they put the entire trading floor, gateways, market data, and risk on Zing, and that's now we've got that sort of relationship. And the things that used to scare them are gone. They're very comfortable now running at very low latency throughout their trading days, with no extra pain for the people that used to have to figure out, well, what's happening in this GC log? Like, what's this spike? What's that mean? All the spikes are gone. And here's a specific case that they shared with us so much that they gave a talk. Our Azul person and their LMAX person on stage together, and we shared this extreme example. On January 15th this year, the Swiss government made an announcement about the valuation of Swiss francs relative to the euro. So that gold bar right there represents minutes after the announcement came out. So the chart is the volume of trading pairs between euros and Swiss francs. The trading floor had a 7 times load increase from normal for that. So the systems got suddenly pounded. Unpredictable, you didn't know it was coming, you couldn't really forecast what the impact was going to be. And even after the immediate spike, the exchange still stayed elevated for the next few hours because there was high volatility. Zing under their exchange kept it running. Not a single problem, not a single outage. No penalty at all that can handle that burst load. And it turns out the burstiness and the responsiveness in the wake of burstiness is not just single events, it's every day. This chart, we like this chart a lot. Basically, they took a whole trading day and for every second of the day, broke it up into 1,000 milliseconds, and then counted in each of those, like millisecond 1, millisecond 2, millisecond 3, the transaction flow. So this is like a histogram of the day, of the trading day. And what this showed us is traffic is regular traffic, not even the bursts. Regular traffic is spiky and bursty. You see that there's 4 spikes throughout the day. Those 4 spikes happen on the edges of every quarter millisecond. There's something out there in the market that's hitting them like clockwork, rolling over every quarter second, and that's those big spikes. The 10 little spikes, same thing. Some other process is hitting them every 10 milliseconds. So, every 100 milliseconds, every 10th of a second. And if you presume that your traffic was flatlined, like not bursty at all, it would be that red curve. So, down at the microscopic level, there is incredible volatility. That if you're trying to keep up with rates that are 15 times potentially higher, because this is an average over the day, you have to either scale for burst, or you have to have something that can handle that sort of high-speed, fast response traffic. And again, you know, if it was nice and smooth and flat, it would be a lot lower than those spikes. So, I mean, that's trying to share some real world examples of where Zing works the way it's supposed to, taking away the things that attribute to pauses and knocking your latencies down to very reasonable levels in terms of the workload at hand. And it's not just theory. We actually harp a lot on how you can properly measure latencies and discuss them in terms of requirements, discuss them in terms of percentiles. You have your bulk traffic, which is fine. We saw that earlier, 60 microseconds was the normal case. But the 25 or the 100 or the 300 milliseconds worst case. There's a whole range in between. There's the worst and the best, but then there's also the 90th percentile, 99, 99.9. So we like to see that dynamic spread of not just the absolute very worst case, but how frequent they're happening throughout a time block. Yes?
You guys architect it in such a way where you just eliminated intermediate nodes and just go straight from point to point and cut down your latency?
No, that's not it at all. There's no change to the question.
Do you do that?
Okay, the question is, do we go direct? The answer is really no. We are explicitly designed with two major differences, well, three. One is we rewrite the memory mapping to use our own pages in memory in the Linux basement down at the kernel mode. So very fast memory switching. Number two, we take advantage of multiple cores, and GC's running on some cores, and Java threads are running on other, and we're very...
Does that do with more the communications architecture, not the internal? Does that do with the communications question?
In terms of the exchange, no. It's not a communications thing. This is stalls inside of the Java virtual machine itself. There are other sources of latency, networks, disks, memory, bottlenecks, but the JVM itself, regular stock JVMs, even with tuning, have this inherent pause time. We're talking about removing that as a player and then seeing what the benefits are after that. Can you go to higher memories? Can you go to fewer parallel nodes because each node can take on more? In this case, in the last case, the floor of the exchange already uses a very sophisticated lockless queuing architecture. It's called the disruptor framework. So they're already doing some sophisticated code. The question is, how can they get other things out of the way of flow? And the JVM pauses, suddenly, when everything else gets better, the JVM pauses become dominant. You take those away, something else becomes dominant, but at a much lower level. It's usually Linux or it's other factors. Which I don't know that we'll get to that here, but does that help?
Yeah.
Okay. One more question?
Do you have to contribute your changes back to the GPL, like Java Open anything? Do you have to, or I'm not sure what the license is on that.
That's a whole topic. Can we do that? Save that for later?
Sure.
Okay. Zing is only Linux. It's built specifically today for the Intel 64-bit architecture. So that's the one constraint. Yeah, in the back.
Does it require running on a custom Linux kernel?
No, stock kernels. Stock, we support the common Linux distros, Red Hat and its cousins, Ubuntu, Debian, SUSE, Oracle Linux, and all of those on-premise with certain hypervisors and with certain cloud architectures as well, predominantly Amazon. Last one. We got a whole block for Q&A at the end.
How often do you do security patches?
We follow the security patch cycle that OpenJDK does with quarterly updates. We usually track, sometimes we can hit it because we have a major release that goes out. Otherwise, we follow up with a point release within, it's not days, but it's not years either. It's more like weeks. Okay. So we just kind of went through the whole universe of latency and the product and how it behaves. This is now sort of a question of proof and in measurement of Cassandra. We want to get to that point. We've done a lot of Java stuff. Let's hop into the Cassandra pieces. So when it comes to measuring latencies, I showed you the time series above already, where you're actually graphing the pause times throughout a time block. And the bars, the percentile bars showed you sort of the values at those percentiles. But now on the bottom, we've taken it and said, let's actually draw a histogram. You know, a histogram is a bunch of bins, and you put the counts of each bin. So in this case, it's a dynamic histogram. It goes from 0% or 50%, which is the median or the bulk of your traffic, up to the 99.9999, and lets you zoom in and see, well, what are the spread of latencies? Latency is not constant. Latency and times are bursty, and they have different frequencies. So this bottom chart shows you, yeah, the red bar is still the max. But now you can see every latency throughout the spectrum, not just the 4 colored bars up above. Does that make sense? So this is, we call this an A-B test. Product A, product B, which one's better? And the better is subjective, but I'll show you why. They both look spiky. They're both, it's 3,500 seconds worth of duration. It was the same time trial. Both of the frequencies of latencies have about the same shape, so they get worse up at the high 9 percentiles. They look really good, really low, down below 99. Right one looks a little bit better. But can anybody notice the weird thing about these two graphs?
Scales.
Y-axis scale, very good. If you zoom in on the y-axis, this 1 gigabyte live set in an 8 gigabyte heap. So we're not talking really big, or 8 gigs is actually pretty normal for a heap. Worst case latency of 13 seconds. And on the right, running Zing, the same portal application, worst case 20 milliseconds. And if you do the percentiles, you can see that, yeah, okay, the Oracle starts to break at 99, but oh, well, hold on. Zing isn't breaking until 49, so 99.99. And if you actually did plot this A-B on like-for-like scales, Zing doesn't even show up. The latencies are that good across the whole spectrum. So that's a boring thing to show people. Like, yeah, look, isn't that great? And you're like, I don't see it. What am I supposed to see? So going back, I mean, there still are pauses happening. We still have some little spikes. It's not all clustered down at 0, but those spikes are usually no longer garbage collection. They're some other phenomenon in the JVM. And we like to beat on those next. Now that we think garbage collection is cured, we're into things like the JIT compilers and other areas of latency to try to bring that floor down even lower. 20 milliseconds is usually great for some applications, but it's not enough for the trading floors. They want some millisecond or better. And an 8 gigabyte heap, I'd like to say we eat that for breakfast. We can go much higher than that. So, other aspect here, the way Zing is designed, it's a dynamic system. So it calculates ahead of time how much time to spend garbage collecting based on how fast you are allocating. And it reserves enough of its own space and threads to do that. In a normal garbage collector, it's up to you to figure that out. What are my ratios? What's my tenure? What's my survivor ratio? What's my new gen size? What's my old gen size? It's really you get a lot of knobs to twiddle, but what is the right way to do it? We like to think that our way is better because, again, it's dynamic. It's figuring out what it needs to do. There's only one thing you need to do to know how to tune Zing. Set your XMX. Pick your heap size. How big do you want it to be? And even when you pick your heap size, this is 40 gig. You can now, as of the build we're shipping tomorrow, you can now put 1 T. So right in your XMX variable. And the beauty of that is, our design is to actually allow you to use your whole XMX, and then there's more. We have a contingency buffer as well. So if you have spikes that exceed your XMX, you don't crash or you hit an out of memory. You actually keep going. Your performance might take a little pinch, but you won't crash on the floor like other JVMs might. But anyway, that's supposed to be a testament to tuning GC just became very easy as well. If you still want to twiddle knobs, there's tons of other factors you can govern, like especially with compile and other things. But for GC, that's it. Set the size. Yeah.
Why should I specify X max? Honestly, isn't it the 19th century kind of technology or option? Why can't you figure out what is my maximum? Like .NET Microsoft CLR does. Why can't you do that?
This is the thing that lets you govern how much is allocated to your
Why can't
process.
JVM be smart enough to govern that? When Microsoft does that, because everyone is bashing Microsoft, but Microsoft does it better than this actually. I use both Java and Microsoft. I run into all these kind of fine-tuning these issues. Why can't Zing or other vendors can be smart enough like Microsoft to manage this memory?
Great theoretical question. Normally, this is set this way because of the hardware you bought is a certain size, and you want to dedicate that process to something. You want to dedicate some other size to something else. So it's not the individual process; it's the balance of the system that's you're trying to not collide with. We normally say make it 3/4 the size of the installed memory. You'll be fine.
That's exactly the problem I'm talking about. I don't want to do anything. I want JVM to be smart enough to do that, which Microsoft does very well.
Okay.
I don't know why the whole Java world nobody's getting it right. I don't know.
Okay. Good. Can we move on?
Yeah.
Good. I mean, I don't knock Microsoft for what they're doing. I trust what you're saying is accurate. I haven't gotten into the CLR as deep as I am into the JVM, so can't speak to better or worse. Anyway, so back to sort of conclusions. Dominant use cases, you can use real Java. You can use as much memory as you want as long as you set the value. And you can, and regular developers can do this work using standard tools. And it's not just Java, the source language, it's also Scala. So what do the latency sensitive Cassandra workloads look like? And by Cassandra, I'll say data stacks, the whole server, because a lot of those components come into play. But just the basic things on Planet Cassandra, if you've got a product catalog where you want fast retrieval, or if you want to do any personalization on the fly, where you're pulling in data from lots of sources quickly, great use case. Fraud detection, very common. We actually have a customer using Cassandra to do authentication requests. So again, backed up by the fraud detection part. Any sorts of messaging is a good case. And anything to do with IoT and gobs of sensor data coming in, where you want to make sure that those latencies are kept low. They're all decent candidates. In terms of deployment, we actually have a couple of customers doing these next sort of scenarios where you've got your Cassandra nodes at the bottom and your Spark nodes on top. You get the best latency situation for both the RDDs in Spark as well as the replication in Cassandra without those hiccups causing potential pressure. And then same is true for Solar. Solar is actually probably one of our most popular use cases with or without Cassandra underneath, but it's a good mix of data storage and persistence and then retrieval across wide swaths of memory. Okay. All right, I'll blast through these last things. So this was sort of like the big picture shot of Cassandra. We've done a white paper where we actually set up a 3-node Cassandra cluster of our own, and we did a punishment test and came up with these sorts of max outlier latencies across the cluster. And again, based on the load we applied, saw the other JVM getting worse and Zing holding its own. So this is a summary over many runs. I don't know that I have time to go into Cassandra Stress 2 because I've got only a couple minutes left. But anybody use Cassandra Stress yet? Tool to load up your Cassandra database? Okay. It's apparently a tool that comes. It's available to test your cluster and its throughput. This is where the damned lies lie. So I at least have to make a point. There's a phenomenon in measuring tools where you set up a load tester and you bang it against the system, and all is good. You're hitting it relatively fast. It could be every second, it could be every tenth of a second, whatever your pace is. But if the system under test has a pause that lasts longer than your sample duration, you actually wind up missing the samples that should have landed during that point where the system was frozen. The name for that phenomenon, we call that coordinated omission. Real samples are omitted from your data set because they never happened, or they never got tabulated. What that means is you wind up with a latency spectrum in the red case where this is actually an intentional pause. They stop the system with a SIG-int, SIG-con, stop and restart. And it says, oh yeah, I got this pause, that pause, that pause. But in reality, they missed all of the other intermediate times in between for that sample rate. So this is why we think Cassandra out of the box lies. It doesn't show you the actual lost samples, versus we've actually modified it to come up with one that accounted, not in the load. The load generation, the load bearing was fine. It's just in the computation of your latency profile. And here's again another case of, what's presented as fact looks like we saw before. There's some scatter, but a couple of big spikes. And if you compare it with hotspot, okay, you got some scatter, got some big spikes. But when you do it side by side, you realize that the correct values are wildly different than the uncorrected values. In the uncorrected case, we have 2 to 3 milliseconds as the 95th percentile, whereas in reality, the hotspot case is more like 500 milliseconds versus 3. So that's the kind of thing we have to be extremely careful for when showing latency profiles, that the tool that you use measures them properly and doesn't omit those intermediate stalls, or those intermediate samples that never got collected. And then this is sort of a long train of latency throughout a run, because if your system is saturated, you're not even firing the next sample on time. So your actual real-world latency accumulates. Wrapping up with the CAP theorem, we just like to think that even though Cassandra fits the availability and partition tolerance factors extremely well, we think it can do better, and that's on the consistency side. By taking away those pauses, those gaps, those time hacks, we think you can actually remove the partition barrier that's falsely put in by having an unavailable JVM. And then, so that means last contention over last right winning. So we defy the CAP theorem. And we don't want you to ever have to face, time running backwards or partition, these, fake partitions, and avoiding any doom zones where your data is now suddenly missing because of the wrong time stamp. Okay, that was a lot of data really fast. We good? Interesting? Worthwhile? So that's the takeaway. Now my last second marketing pitch, and before I leave the stage, we do have some hot things going on in Azul. Like I said, 1505 is imminent. It's RTMing tomorrow. It's our 1 terabyte heap support, among other things. We do run on the cloud, in case anyone's interested about that. We've got Amazon EMI set up. We're working on Docker as a future release item. Our Cassandra paper's on our website. That's been up for a couple weeks. And although we don't have anything written about Spark yet, that's the next thing I want to tackle, because I do have a couple of people in our open source program that are using Zing under Spark. And then our Zulu is a whole other topic. That's also got a build that's going live this week. It's the end of the line for Java 7 from Oracle's perspective, but we're just getting going. We take over custody of the 7 OpenJDK line with Red Hat from here on in. And go get some Zing. Our Central American or Central Region rep, Elaine Sanger, is in the audience. If anyone wants to talk about it at all, set up maybe a trial. I'll be here. I'm actually speaking tonight at the Java user group out in Town and Country. If anyone's interested in coming for a completely different topic but still around Zing. And then I put some cards for the free trials out near the drink table. If you want one, grab one. Otherwise, Elaine's got some, or I've got some. And then the big question: gooey butter cake or the concrete? I have one night in St. Louis. What do you recommend?
Concrete.
Concrete? All right.